Hello everyone, my name is Sergio Sevillano. Thank you very much for watching my talk. I'm a postdoc right now at the University of Pennsylvania, but today I'm going to be presenting some work that I've been doing in my previous postdoc in Durham University. And that work is screening mechanisms from a neutrino perspective. So first of all is, why do we need screening mechanisms? Well, the main reason is that here we are kind of studying dark energy and we have some motivation for different theories of dark energy because of DESI or Hubble tension or other type of tests. But all in all, it really seems that there is some type of, motivation for scalar fields in our universe. And every time you have a scalar field in your universe and a theory of gravity, what will happen because of just effective field theories and changing the energy scale of your theory is that you're going to start generating this type of couplings. For example, here you see that normally we have some theory of gravity. This is a constant term. This is Einstein's gravity. And we also have some type of scalar field with its potential, its kinetic energy, and the normal stuff there. Well, in the end, you're going to end up naturally having also to consider these terms over here. There are nothing but what we normally call extensions of gravity or modified theories of gravity, or there are many different terms. Specifically because here we are coupling gravity, which is a tensorial mode, with a scalar field, these type of theories are called scalar tensor theories. And you can have, in theory, any type of coupling like this. There are some of these that we already know that they are not possibly there. And the main reason is because of the speed of gravity. If you start including terms like this, what is going to happen in the end is that you're going to be changing the speed of gravity. And we know that the speed of gravity has to be very close to the speed of light or equal. So here I'm only going to be considering those theories where the speed of gravity is still equal to the speed of light. This leads to the following Lagrangian, that is nothing but the Brans-Dicke action that many people like. I guess that is the simplest modification of gravity, because what it does is having some scalar field, phi here, and couples it to the Ricci scalar. This is a non-minimal coupling. You can also have some matter Lagrangian, that in our case is going to be the standard model that we know and love. And the only important thing here is that we can see already that the field phi should not be varying too fast nowadays. And the reason why that happens is because this term will give you the Planck mass today. So in the end, what we want is something that goes like effective expansion, like a Taylor expansion of 1 plus some correction. And we are going to be studying for that correction. Now, having that correction is not something that normally is small. Actually, can introduce a big effect on your universe. And this big effect is usually called field forces. So in the end, these type of couplings are going to give you this type of kind of field forces that look like gravity in a way. And the reason why they look like gravity is because the charge of these field forces is the mass of the particles involved. Or for example, if it's not particles, it could be just two massive bodies. You can see that you're going to have this potential. So the potential, you can see that normally we have the Newtonian potential is the one here, and these type of couplings are going to give you the modification of gravity, and that is this new term over here. This modification of gravity depends on two parameters, at least at linear order, and it's a Yukawa type coupling. The first parameter, alpha, is the strength of this coupling, and lambda is related to the scale of this coupling. So it's in a way related to the mass of the propagator of this field phi. You can see that we already have a lot of bounds. This is kind of, recent, this is 2020. And most of the bounds, what ends up saying is that this type of field forces cannot be too strong. So you can see that if you go to high here in alpha, then we already have constraints on this type of forces. Or also, what it says is that it cannot be too long range. So the more long range, the most constraints we have. So you want lambda to be either very small or alpha to be also very small if you want to kind of evade this type of constraints. Now you already see here that this is a problem because, we are going to have some scalar field that can be related to dark energy, dark matter can be related to many different things. But in the end, given a potential, you can already know if this field is completely constrained or not. Unless something else happens, and this is exactly what the screening mechanisms are going to do. They're going to give us some wiggle room for this type of theories in a very natural way, and they are actually very cool. So screening mechanisms, what they do is use this interaction that we have here in our advantage, or in the theory's advantage, if you will. If we take the equations of motion for this equation, are going to take just the equations of motion for gravity and the equations of motion for phi, and you can see that for gravity we have some type of modify the equation of motion here. That is, you can see that this is the Einstein tensor. So in a way, it looks like Einstein's equation, but not really. But most importantly, when we look at the equations of motion for phi, what we find is the usual Klein-Gordon equation, but we have one extra term, and this extra term depends on the background's Ricci scalar. Luckily, we can calculate what is the background's Ricci scalar because we can take the trace of this equation and solve for that. Doing so, what we find is that the background's Ricci scalar only depends on the background's density over F. So in the end, we can just substitute the Ricci scalar for the background density to get some type of effective potential for phi that depends on the background density. This means that some of these characteristics that I was mentioning earlier, such as the strength of the interaction or the scale of the interaction, will now not only depend on the potential, but also on what the background's matter distribution looks like. And the most famous two models that do this is the chameleon model that use this type of, this environmentally dependent potential to increase the mass of the propagator in very high density regions. And then you also have the symmetron model that is very similar but kind of different, that instead of changing lambda, instead of making the potential more, the field more massive, what it does is change the strength of the interactions. And the way the standard model couples to this field is kind of simple. Well, this is the theory that I was showing you before. I have changed a little bit this function, but it's the same type of function. And the most important thing that you need to know here is that there is a trick to make this theory look a little bit more, more easy to work with standard model particles. And that is that you can take a conformal transformation. If you take this conformal transformation, basically you kind of change the metric in such a way that you recover some theory of gravity that is canonical, the Einstein's theory of gravity, but all these interactions now take place, appear inside your standard model. I don't want to go through all this derivation because actually it takes quite a long time, but all in all, what happens in the end is that this theory is effectively equivalent to having some standard model theory where all the masses depend on this function a of phi. This is what we are going to be looking at, because when you are inside a screened region and outside a screened region, because the field vacuum expectation value for phi is changing, we can hopefully measure a change in the masses of elementary particles. And doing that is how we are going to be hopefully constraining scalar tensor theories. For that, we're going to have this setup. This is a true picture, a real picture that they took of me. It was quite cold out there. And you can see that this is kind of like the basics of what we are going to be doing for part of the project. As I'm saying, depending on the background's density, the field phi is going to change. And because the field phi changes, that changes the mass of particles. If you change the mass of particles, actually you're going to affect their geodesics. Now, we may wonder now what type of particle we want to use for this. And of course, normally to do astronomy, we use photons and they work really well, but this is not going to be a good candidate now because we want the mass of these particles to be changing with the space. And because the photons are massless, there are not going to be any effect on this. So that's actually bad because we cannot use photons to measure this effect, but in some way it's also good because then we can use photons to calibrate where this interaction is taking place. Say that we are looking for some object, we can calibrate how far this object is by using photons, and then we can see any effect by using massive fermions. The only problem is that we cannot take massive fermions that interact very strongly with the medium, because if there is some gas in the middle or some planet or whatever, then we don't know if we are seeing, for example, some difference in the geodesics because of these field forces or the screening mechanisms, or because of its interaction with some gas or a planet or whatever. So there is only one candidate that is massive and also interacts very weakly with absolutely everything it encounters with, and that is neutrinos. So that is basically what we are using neutrinos for this, and that is this work over here. As I was saying before, I did this when I was in postdoc in Durham with Arturo Di Giorgi and Ivan Martinez Soler, and it was quite a nice collaboration, just to mention that. So we looked at mainly two things. The first one was trying to see if we can measure any effect on the mass of neutrinos, like any variation in the mass of neutrinos locally in Earth with their mass in vacuum, by using the supernovae SN 1987. The reason we are using this supernovae is because this is the only supernovae that we have so far measure both photons and neutrinos. So we can use photons to know how far is the supernovae, and with that we can infer the mass of neutrinos as they, depending on how long it took to arrive to us. But actually there is something very cool that happens with this, and is that neutrinos, when in a supernovae, they are always emitted exactly at the same time, independently of their energy, because supernovae, they collapse, and when they collapse they become very opaque, and it's not until they explode that all neutrinos that are inside, completely kind of confined, are able to leave the supernova and reach to us. So all neutrinos, independently of their energy, leave exactly at the same time. However, there's something very important, that is that two neutrinos with the same mass but different energies are going to arrive to us at different times, because the most energetic neutrino is going to move a little bit faster than the least energetic neutrino. And the good thing is that this was already used to measure the mass of neutrinos in vacuum already. And they put an upper bound of 6 eVs. This is quite a high upper bound compared to the other laboratory tests. But this is really great, because now we can recast this solution, basically this bound on the mass of neutrinos from supernovae, against the test this against the, or compare it against the bound that we have for mass of neutrinos here on Earth. And because we know, like if Earth is completely screened, we know that the mass of neutrinos could be different inside Earth than outside Earth, then we can see or test for this rescaling of masses by comparing these two values. You can see that in this equation over here, we are already including this A of R. So basically we just have to change A of R in this function to see how much is the rescaling that we find for different theories of gravity. In order to do that, we actually have to be aware that the universe is not a vacuum. There is stuff in between this supernova and Earth. And the stuff that we find is between is two main things: dark matter and baryonic matter. Now, baryonic matter is shaped in the way of this galaxy that is the Milky Way, so it's going to have shape of a disk, while dark matter halos are going to have this shape of spherical symmetry. And not only that, but something that is very important is that also we were lucky because this supernovae is not actually inside the Milky Way, but a little bit outside. It's in a different dwarf galaxy that is orbiting around the Milky Way, that is called the Large Magellanic Cloud. I think that I got that right. But it's basically 51 kiloparsecs away from Earth, and that's how long it took quite long to arrive to Earth. We were able to take different profiles, because we have from different tests, I put here the reference, different tests for what is the dark matter distribution between inside Earth and between the Milky Way and the Large Magellanic Cloud. And this is the plot that you are seeing here. This is the density distribution of dark matter, and this legend over here corresponds to 10 to the minus 22, 10 to the minus 23 in grams per centimeter cubed. And actually this is the other way around for some reason. In the end, when you take like the line of sight of what is the average dark matter density throughout the line, like the propagation that the neutrinos had, you can get this estimate. But just to be safe, what we did, because also it makes the calculations much easier, is to take some conservative constant estimate, and in the end what we took is this value over here. But in the end, you can do that, and that's what this value A comes in, and the mass of neutrinos comes there. And for M0, what we are taking is the mass of neutrinos as measured independently in some other lab inside Earth. And for that, we are taking the best one that we can use so far is Catherine constraints. And the reason why that happens is because they are measuring the same flavor neutrinos as we would measure other, like that are emitted, from the supernovae. So the bound that we are taking is 0.45 eVs. And this limit that you see here is the one that we are taking from this other work that I was mentioning before. Right now it's in 6 eVs more or less, but in future prospects it's estimated that with more supernovae we can get a better constraint of that number, and it will go down to 0.06 eVs. So we can really improve this number. Having this in mind, then what we're going to be doing is, instead of just saying that basically we don't want the mass of neutrinos to be larger than that in vacuum, we want to be, again, a little bit more conservative and talk about just the errors of this, or the difference between these measurements, to be smaller than the measurement done with the neutrinos in vacuum. All right, before showing you the constraints from this, what I'm going to be doing is also going into a different test that we did is that comes from flavor distortion. As you may know, neutrinos are very interesting also because their propagation, like their mass eigenstates and their interaction eigenstates with the standard model are not the same, are not parallel basically. There is some offset. So the way they propagate through vacuum is not the same as they interact with the standard model. And this has been used to know that neutrinos are, like, to put some constraints on their masses, but also on knowing how they oscillate when they go through Earth. So there are two big effects that we are going to be considering here. This, again, the equations took some time to derive, but we can talk about this in the questions day, whenever we meet. But the main two things that happen when we change the mass of neutrinos is that as they go through Earth, the mass of neutrinos are and elementary particles in different parts of Earth is not going to be the same as we think they are from local tests in the surface. And doing so, what is going to happen is that the number of electrons in Earth will depend on the mass of particles. So maybe there are more electrons or less electrons, so they are more likely or less likely to interact. But also the oscillation wavelength depends on the neutrino masses. So basically, if the neutrinos become very, very light, they barely get to interact with any electrons inside Earth. So that is something that we can use to place bounds on any type of screening mechanism. A given example for this that was done by Ivan, well, Ivan did all this calculation. He used 9.3 years of data from IceCube. And you can see here, for example, the difference between the data, there are these points, and the standard model type of interactions, that this is the blue one, the 3 type of oscillations, and the no oscillation case. So you can see that the scalar tensor theories, when you have a screening inside Earth, what it's going to do is take your normal theory and push it a little bit to that direction of having no oscillations. Why is that? Because what happens is that the neutrinos are becoming less massive, and because of that, they are interacting less with whatever there is inside Earth. So basically there are less oscillations. For this, we have to now model what is A of R. And we have, as I said before, 2 models that we are considering. That one is the chameleon, and the chameleon looks something like this, although this is something also mentioned as the dilaton chameleon. What happens, you can see that the potential is something like an exponential, and then we have this function V, that what it's going to be doing is pushing this effective potential, or the vacuum expectation value, to more and more negative values. So in the end, what is happening is that you're changing the mass because you're squeezing more and more the effective potential. And what the symmetron is doing is kind of, again, similar because there is some environmental dependence, but you can see that you go from some value to another value. So you have the double wall potential, and in high enough densities, you restore the symmetry. That's where the name comes from. And you go from this vacuum expectation value to the vacuum expectation value at 0. We will compare these two things. So these are the bounds. Ta-da! So here we have time delay being red and flavor distortion being blue. We can already see, I'm going to kind of talk over these plots, that for the chameleon, all these bounds are not very good. And the reason why that happens is because the chameleon, what it does is always having some type of Yukawa type coupling. But you can always kind of make up some new experiment that fits in within that scale of the interaction and measure field forces again. So that's something that you can do with the chameleon and has been done a lot. So in the end, this type of tests that we are doing are not good enough. So that's what we are finding here. However, for the symmetron, that doesn't happen. In the symmetron, once you have some screen theory, the linear coupling completely disappears. So you only have quadratic couplings, and it's more difficult to measure. You can see that, well, these dashed lines that I have in these plots basically mean that the rescaling of masses is larger than 100%. So with that, the conclusion from this plot that we see is that there is something very good from this test that we are doing, and is that neutrinos are going to measure all the different shapes that you have from the potential, like a strength potential that I'm talking about. So it doesn't matter if the interaction is very short range, because we are integrating over throughout the whole line of sight of neutrinos, like all the propagation that they had. It doesn't matter if the strength is very short, because we are going to measure, because we are going to integrate through that. With that, I hope you like this talk. Here is a little bit summary. Basically, we are using neutrinos to see for any difference in the geodesics from modified gravity. And we are finding that using both supernovae and flavor bounds, we can get some new constraints that weren't there before. So I hope you like this talk. Thank you very much for watching and paying attention, and I hope to see you there in my session whenever I'm answering questions, and I'll be very happy to answer your questions. Goodbye.